that we would go over that same example last time, but in the other way. So I do think that's a good place to start, just so you can see that either method you use should end up giving you at least the same points. It might not always be easy to tell if the thing you're finding is going to give you a maximum or a minimum, but at least the processes, if either one is applicable, should yield the same result. So let me go ahead and write down a few things here. I'll remind you that last time the problem we were talking about was you're trying to mail something, right? We want to mail something and we have a constraint that is that the length plus the girth has to be less than or equal to 108 inches. So the length plus the girth has to be less than or equal to 108 inches. We drew a picture of a box that we might be mailing. Point of note here, when you're drawing a picture like this, and you don't know what any of the values are, like you don't know that it's a square base, something like that, you should I try to draw it so all the lengths look like they're different lengths, right? So I'm not drawing this as a square, even though I know it actually turns out to be a square when I solve this. It's not super duper important, but you don't want to like trick yourself into thinking two values are the same when they're not necessarily the same. And then, so I'm going to call, I think I called this X, this Y, and this Z last time. So our constraint here is, yeah, sure, is that the length, which is Z, plus the girth, which is 2X plus 2Y, is less than or equal to 108, but we're going to say equal to 108 because we want to use up all the dimensionality that we have. So there's our constraint. And then we were trying to maximize the volume. So we're trying to maximize volume equal to X times Y times Z. And last time we did the whole, the gradient of one thing equals lambda times the gradient of the other thing. We'll do this one relatively quickly just to see that. So I don't remind you, last time the values we got were that X and Y were both 18 and Z was 36. We're going to get the same values here, doing it the more old-fashioned way. Meaning I'm going to take this equation, isolate one of my variables, and the obvious choice here I think is Z, because it doesn't have a coefficient. So I'm going to take my constraint and solve for Z. I'm going to get Z equal to 108 minus 2X minus 2Y. And I'm going to substitute that into my other equation. So that then the thing I'm trying to maximize, I can then write as a function of two variables. So I'm going to have volume as a function of X and Y equal to X times Y times this new thing here for Z. And if I'm trying to find my partials, I'm probably going to multiply this out before I start finding my partial derivatives. All right, so I'm going to find my critical points by taking my partial derivatives and them equal to 0. Before I do that, let's actually distribute the xy to each term and get 108 xy minus 2 times x is 2x squared times y minus 2 times x times y. So that's what we're trying to maximize. So that's what we're going to find the critical points of. So my partial with respect to x is going to be 108y minus 4xy minus 2y squared. Something actually I want to point out here that you might notice. If you look at this equation is symmetric in the variables x and y. What that means is that if you interchanged every x and every y, the equation would still be the same. Right? If I wrote this as 108 times y times x minus 2 times y squared times x minus 2 times y times x squared, it would still be the same equation. I want you to take that in for a second. What that usually almost always means is that if you find a critical point, its pair has to be a critical point as well. Meaning, like, for example, if 2, 5 was a critical point, then 5, 2 would also have to be a critical point because you interchange x and y and get the other point. It also usually ends up meaning that most critical points end up being the same x and y value. So when you see symmetry like this, you can usually expect to get an XY coordinate like 4, 4 or 6, 6 or something where both of them are the same. Not that you need that to happen, just it often happens. If I'm going to try and solve this, I'm going to factor out I should do the other one here first, sorry. Vy is going to be 108x minus 4xy. Feel like, no, Vy, ooh, minus 2x squared, apologies. Over here it's minus 4xy. Now, both of these look kind of terrible. I would probably look at each of them and say that I can factor something out. In this first one, I can factor out a y. I've got y times 108 minus 4x minus 2y. And in the second one, I get x times 108 minus 2x minus 4y. This system of equations has 4 possible solutions, and only one of them is useful to us. So let me point out, you could get x equal to 0 and y equal to 0. And then how much volume does your box hold? Right. So having either one of them equal to 0 is not helpful, but I still want to show you because I don't think we've actually seen one like this. So let me just point out here that when you do this, there's 4 different ways you can get both equations equal to 0. So you can have either factor equal to 0. So one way to get 0 is to have in the first equation y equal to 0, and in the second equation x equal to 0. That would make both equations equal to 0. Or we could have in the first equation y equal to 0, and in the second equation the other factor equal to 0, where the other where the other factor is 108 minus 2x minus 4y equal to 0. But then again, I'm doing too much work here, but I want to do it anyway. And then since y equals 0, we say that that's going to be 108 minus 2x minus 0 equals 0. So you get x equal to 54. Again, not a very useful critical point in this context, because we don't want to have a box that has 0 volume. But if this was just a regular function you're looking for critical points, 0, 0 would be a critical point. So would 54, 0. Now, based on what I said before, if 54, 0 is a critical point, we would also expect 0, 54 to be a critical point, and it is. If you look at setting the other factor in equation 1 equal to 0, 108 minus 4x minus 2y equal to 0, and x equal to 0 in equation 2, then you would end up getting y equal to 54. In the same way we just got x equal to 54 in the previous one. But the thing I'm trying to point out here or stress is that I'm saying that each of these equations can equal 0 by either saying, look real closely here, watch for a second, that this is 0 and this is 0, or that this is 0 and that is 0, or that that is 0 and this is 0, or finally that that is 0 and that is 0. Because as long as one of these two factors is 0, the whole thing multiplies to 0. So that's the way I'm deciding what I'm getting. So finally, the one that's actually going to give us non-zero values for both x and y is setting both the first equation's factor 108 minus 4x minus 2y equal to 0, and the second equation's more complicated factor 108 minus 2x minus 4y equal to 0. And this is the thing you have to solve then for one of the variables and plug it into the other equations. Let's take this equation and solve for y. 108 minus 4x equals positive 2y. Dividing both sides by 2, 54 minus 2x equals y. Substitute that into the other equation. So then I have 108 minus 2x minus 4 times 54 minus 2x equal to 0. Simplify. 108 minus 2x. Negative 4 times 54. Ugh. Whenever I want to multiply by 4 and it seems a little complicated, I just multiply by 2 twice. 2 times 54 is 108. 2 times 108 is 216. So minus 216, and minus 4 times minus 2 is plus 8x. So let's see, I've got 8x minus 2x, I've got 6x over here. 108 minus 216 is negative 108. Or that's going to equal positive 108. finally, dividing by 6. 108 divided by 6 is 18. And if I plug that back in over here, y is going to equal 54 minus 2 times 18, which is 54 minus 36, which is also 18. And then I can actually check to see, is this thing a maximum or a minimum? So I can go back and look at my first partials for a second. Like, okay, well, capital D here is going to be VXX, VYY minus VXY squared. VXX is going to be, let's see, 0 minus 4y minus 0. VYY is going to be 0 minus 4x. And finally, VXY is going to be, ooh, it's going to be a little complicated here. It's going to be 108. Let's say that 108 minus 4x minus 4y squared. And I'm hoping that when I plug in my critical point, that this tells me it's a maximum. Otherwise, I've done all this for nothing. Not really nothing. Okay, let's see. If we plug in the critical point that we actually care about, which is where x is 18 and y is 18, we're going to get negative 4 times 18 times negative 4 times 18 minus 108. 4 times 18 is 72. So minus 72 minus 72 squared. That ends up being, oh God, math. Negative 72 times negative 72 minus 108 minus 144 is negative 36. I don't want to do any more math here. I've done enough math to see that this is going to be positive. 72 squared is bigger than 36 squared. So 72 squared minus 36 squared is going to be a positive number. And then since my second derivative here is negative, that means it's concave up, which means we have a maximum. I'm sorry. I said the wrong thing. I said the wrong thing. Let me back up. Let me back that up just a little bit. fxx is negative, meaning we're concave which way? If the second derivative is negative, concave down, meaning we have a maximum. I said concave up, but that was wrong. Concave down, meaning we have a maximum. Sorry about that. Finally, I know it's right. It's kind of heinous no matter how you slice it. But at the end of this process, to go back and answer the question, what dimension we need? We have x, we have y, but we need to find z. So we go back to our constraint. We say, oh, z equals 108 minus 2x minus 2y. So z is going to equal 108 minus 2 times 18 minus 2 times 18, which is 108 minus 36 minus 36, which is 36. So yes, we do get the same numbers as when we did it in class on Wednesday using LaGrange. Is this better? Who knows? It's a matter of perspective, I guess. The real point, though, is that I would probably do this if I could see how to do it this way. But there are some types of problems that really are less doable in this way. Yeah, questions? No, you're good.
Okay, so solve for D and then we found that D is greater than 0. So
Right.
That's basically proving that it wouldn't be a solid.
Right.
Okay. All right. Because I saw the fxx and then I saw that it was less than 0.
All right, and I should have written VXX here, not FXX, but yeah. But yeah, we were checking that after we determined that D was greater than 0. So D greater than 0, right? That means we have a max or a min. And then checking that VXX is either positive or negative tells us if it's concave up or concave down, which tells us if we have a minimum if it's concave up, a maximum if it's concave down. That's all right. All right, let's look at some more LaGrange things here. Yeah. We'll just try and talk about this process in general. Most of the time, unlike other things, most of the time, if someone wants you to use LaGrange multipliers, they will specify that they want you to use LaGrange, which is good. So let's look at this question. Use LaGrange. I'm not going to write multipliers. We know we will talk about. Use LaGrange to find the point on the plane 2x plus 3y plus 6z, no, plus z, sorry. 2x plus 3y plus z equal to 6 that is closest to the origin. As with any Lagrange problem, there should be something you're trying to optimize, either minimize or maximize, and there should be at least one constraint, maybe two, right? You definitely have a whole second option. I feel like optional is not the right word here. Is this homework really optional? Like, I mean, I guess it's all optional, but like, are you going to be tested on it? Then it's not optional, right? So right in the second Lagrange multiplier homework, there are three problems here that have two constraints, which is, I think, atypical for 17C. Most people don't get into it that much. I can't say it's a good thing or a bad thing, but I haven't seen other 17C teachers go into the two constraint examples, but we can certainly handle it. It's not that much worse. So before we can go anywhere, we have to figure out what our constraint is and what we're trying to optimize. Well, the constraint's given. The point has to be on the plane. So this equation here, 2x plus 3y plus z equal to 6, that is our constraint. People would typically call this g of x comma y comma z. And again, you can kind of do it either way. I personally like to ignore the constant, so I would choose to say, I don't know, what is he doing in class when he says what the constraint is? Is he saying it's the stuff that's equal to 0? Like, can I see? Do you have notes I can look at real quick? I just really want to know that so I can be consistent with how to use it. Yeah. So he's totally setting the constraint equal to 0. Cool. All right, good. So what we should do then, really make it easier to see what's on the board there. So really what I should do, I should say, is not exactly this, but instead we should solve that equal to 0. So g of x, y, z is going to be equal to 2x plus 3y plus z minus 6. Because our constraint is 2x plus 3y plus z minus 6 equal to 0. That's our constraint. And so g is the left side that's equal to 0. There's. And then we're going to find the thing we want to maximize or minimize. But what are we trying to do? We're trying to find the point on the plane closest to the origin. Meaning we want to minimize the distance between our point and the origin. So just to have like a picture here, right? If our plane looks something like, something like this. Here's our plane, right? And there's the origin right there. And then some point on the plane, let's call it, x comma y comma z. We're trying to minimize that distance there. So the distance is equal to the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Has he done any examples with distance? No. Okay. So the fun thing about distance here is instead of minimizing the distance or maximizing the distance, it is always equivalently words. You will get the same point if you minimize the distance squared. So instead of minimizing this, we're going to instead minimize the distance squared, which is just x squared plus y squared plus z squared. And you might see that taking the derivatives there is going to be much less terrible than taking the partial derivatives with the square root there. And that's always true. Think about it. So if you're curious as to why this is true, well, if you make the inside of the square root as small as possible, then you're making the output value also as small as possible. Or if you think about it this way, the square root function is an increasing function, right? If you graph the square root of x, right? If you make the insides, the thing you're taking the square root of as small as possible, then you make the corresponding output values as small as possible. As they get lower and lower and lower. So it's always the better choice to try and maximize or minimize the square of the distance instead of just the distance itself. And that is our f of x comma y comma z. So great, we've got our f, we've got our g, come on in. Now we're going to, he likes to find the gradients of them equal to each other, right? That's how he's doing it. Cool. It is, I feel like it is less writing that way. Good, Matt. You look like you have a question, Maggie. No question? Okay. Well, you're always welcome to ask questions you've got. Isaac, to catch you up, we were trying to find the point on the plane 2x plus 3y plus z equal to 6 that is closest to the origin. So our constraint is that the point has to live on the plane. So it has to be true that 2x plus 3y plus z minus 6 equals 0. And we usually write the constraint in a way so that 0 is on one side, everything else is on the other. That constraint, that 2x plus 3y plus z minus 6, that's what g is going to equal. And then we're trying to minimize the distance to the origin because that's how we find the point that's the closest. The distance would be the square root of x squared plus y squared plus z squared. But it is also true that instead of minimizing the distance, you can minimize the square of the distance, which is a much less computationally terrible thing to do. So that, yes, exactly. Because all I did was square both sides, right? I said the distance squared is equal to that square root squared. And that is always something that you're allowed to do. Instead of minimizing the distance or maximizing, you almost never maximize distance. You can always minimize or maximize the square of the distance, which is always going to be nicer. Really, another reason why it works computationally, just so you all know, let me just show you real quick, because I think this is kind of neat. Just as a point, right? If you had like f of x equal to, I'm gonna make it easy, the square root of x squared minus 8x, and I wanted to find the critical values of that, right? I wanted to find the points that made it either a maximum or a minimum by finding the critical values and setting them equal to 0. Well, if I take the derivative of this, look what happens, and just watch for a second. You probably don't really actually need to write this down. If I take the derivative here, the derivative of the square root of some stuff, or some stuff to the 1/2, is 1/2 times that stuff to the negative 1/2 times the derivative of the inside stuff, which is 2x minus 8. But if you look at this, rewriting this, it's really 2x minus 8 on top over 2 times the square root of x squared minus 8x on the bottom. And you know how I solve this equal to 0? By setting the top equal to 0. You know what the top also is? The inside, the derivative of the inside, right? So if I said instead, do f of x squared equal to x squared minus 8x, and then take the derivative of that, which is 2x minus 8, and set that equal to 0, you get the same thing. That's why it really works. Whether you're trying to take the derivative of the inside of the square root or the derivative of the entire square root, you still end up setting the derivative of the inside part equal to 0. So it works always, which is nice. Okay, but now back to LaGrange here. So for the LaGrange, we're setting the gradient of f equal to lambda times the gradient of g. And I would just get used to really writing it as, right, just all the partials, right? It's going to be fx equal to lambda times gx, and then fy equal to lambda times gy, and then fz equal to lambda times gz. So here, and then I should also say, and g equal to 0. Right, that's our fourth equation, is just the constraint equation that we already started with. So we're going to get, let's see, fx is, these are going to be really not too bad. So fx is going to be 2x equal to lambda times gx, and gx is going to be 2. Fy is 2y, gy is 3. So 2y equals 3 lambda, and fz is 2z, and lambda times gz is 1. So just lambda. And finally, we could write the constraint over here. 2x plus 3y plus z equal to 6. There's so many different ways to do this. I personally would do the following almost every time. Solve each of these equations for lambda. That's what I would always do. So lambda equals x, and lambda equals 2/3 y, and lambda equals 2z. And then set any two of them equal to each other. So if we set these two equal to each other, we're going to get x equal to 2/3 y. And then pick a different two. Not the same two you just picked. You still have to pick one of the ones you already used. Pick these two and get 2/3 y equal to 2z. Observe which variable comes up twice. In this case, because of what I picked, y came up twice. So isolate the other variables, meaning I've already got x equals 2/3 y. I'm going to divide both sides by 2 here to get z equal to 1/3 y. Take those, plug them back into your constraint. So then my constraint is going to be 2 times 2/3 y plus 3y plus 1/3 y equal to 6. I could try to get the common denominator, but that seems silly. Let's just multiply both sides by 3. So if I multiply everything by 3 here, the 3 goes away, I get 2 times 2y. 3 times 3 is 9y. And then 3 times 1/3 is just 1y equal to 6 times 3. So I have 1 plus 9 plus 4, so I have 14y equal to 18. So y is going to be 18 over 14, which reduces to 9 over 7. And then I can go back and find z. Z is going to equal 1/3 times y. So 1/3 times 9 over 7 is 3 over 7. I can go back and find x. X is going to be 2/3 times 9 over 7, which is going to be 2 times 2 times 3 over 7, so 6 over 7. And I don't really see the value in it, but if you wanted to, you could also note that since lambda is equal to x, lambda should equal to 6 over 7. I don't see why we would do that. Some people do this thing where they like write everything in terms of lambda and then solve for lambda. In fact, let me just point that out because, okay, that's fine. So let me back up here for a second. The answer to the question here, the point that is closest, so the point 6/7, 9/7, 3/7 is the closest to the origin on our plane. But just, yeah, I suppose that works just fine. So the real thing I'm trying to get at here is there's more than one way to do this. I could have, if I'd wanted to, although I really, really don't ever want to solve for lambda, I could have solved each of these for lambda. I'm not using the right word. I could have solved each of these in terms of lambda, meaning x equals lambda, and multiply both sides by 3/2 to get y equals 3/2 lambda, and multiply both sides by 1/2 to get z equal to 1/2 lambda, and then plug all of that into your constraint. So then the constraint, which was 2x plus 3y plus z equal to 6, then becomes 2 lambda. 3 times 3/2 lambda is 9/2 lambda plus 1/2 lambda equal to 6. Hopefully this works. 9/2 plus 1/2 is 5. 5 plus 2 is 7. So 7 lambda equals 6. So lambda equals 6/7, which is what we got over here. And then you go back and plug in lambda into each spot there and you get x, y, and z. That's also a way of doing it. It's just never the way I've really done it. That doesn't mean it doesn't work. It just feels wrong to me. Questions before we move on to another example? Okay. here. Sure. That's a good one. I like this example. And then after this one, we'll do some two constraint examples, at least one. The temperature, capital T, on the ellipsoid. What do you think of when you think of an ellipsoid? What's that? How about an ellipse? What's another name? What's another name that starts with the letter O for an ellipse? An oval. An ellipse is something that looks like an oval. It's like a circle that's been stretched in one direction. An ellipsoid is like an ellipse or an oval that's been rotated to have three dimensions. I usually think of, although it's not a perfect analogy, I think of an egg. An egg is kind of an ellipsoid, not really because it's pointier on one side than it is on the other, but oh well. It's still good enough. So the temperature on the ellipsoid given by x squared plus 2y squared plus 3z squared equals 30 is given by the equation temperature at x comma y comma z equals 2x minus y minus 3z. Find the hottest and coldest point. On the ellipsoid. So it seems like just looking at this equation here, to find the hottest point, you would want a positive x coordinate and negative y and z coordinates. And to find the coldest point, you would want the vice versa of that. You want the negative x coordinate and positive y and z coordinates. That might necessarily happen, but just something I'm seeing when I look at this equation. Usual process. Identify your constraint, identify the thing you're trying to maximize. So we're trying to maximize T. Let's call it, even though I usually call it F, since he already called it T here, we're trying to maximize T equal to 2x minus y minus 3z. Notice that the thing we're trying to maximize is not equal to a number. We don't know what value it has. If it was equal to 7, then you couldn't maximize it because it's always 7. So whenever you're trying to maximize something, it shouldn't be equal to some actual numerical value. It should just be some function of your variables that we're going to deal with. On the other hand, the constraint is equal to some number. I've got x squared plus 2y squared plus 3z squared equals 30, or as I'm going to write it, x squared plus 2y squared plus 3z squared minus 30 equal to 0. And this is what I'm going to call my constraint. And let's call it capital G just for fun. And now we do the thing. We take our gradient of the thing we're trying to maximize and set it equal to lambda times the gradient of the thing we're constrained by. So Tx equals lambda Gx is going to give me 2 equal to lambda times x squared. Sorry, times what? Not times x squared. What should I be multiplying by? Trying to find Gx. What's the partial derivative of this with respect to x? Thank you, yes. Don't let me get away with things like that. Ty equal to lambda times Gy is going to give us -1 equal to lambda times 4y. And finally, Tz equal to lambda times Gz is going to give me -3 equal to lambda times 6z. And yeah, I'll say again, even though it's not my thing at all, you could totally solve each of these in terms of lambda, right? If you wanted to, you could say from this equation, you're going to get x equals 1 over lambda. Here you're going to get y equals -1 over 4 lambda. And here you'd get z equal to -1 over 2 lambda. And then you can plug all those into the thing that's your constraint and then solve for lambda. And God, I hate that so much. It's a personal bias. That is a totally fine way of doing it. I guess it's a pretty good way of doing it. I don't know. I don't like it. So but that's one way of doing it. Or we'll do it the way I want to do it. And then if you really want me to do it this other way, we will. What I would do is I would solve each of these for lambda. So I would say in the first equation, 2 equal to lambda times 2x is going to give me, well, isolating lambda, I'll get 2 divided by 2x or 1 over x equal to lambda. And then similarly, -1 equal to lambda times 4y is going to give me -1 over 4y equal to lambda. And finally, -3 equal to lambda times 6z is going to give me -1 over 2z equal to lambda. No, I might be becoming converted to the other. Like they're both good, but I do feel like this maybe requires more thinking. Because the way what I'm about to do now is I'm about to set these two of these equal to each other and then try to get a relationship between x and y or y and z. And let me pick 2 different ones than I did last time, just to kind of not always having y be the thing that shows up twice. So let's say we pick these 2 equations. Let's say we pick the first equation and the third equation to give us that 1 over x equals -1 over 2z, or cross multiplying. Sure. 2z equals -x or -2, let's say -2z equals x. And then picking the first and second equation, using a different color. We're going to get 1 over x equals -1 over 4y. And then cross multiplying, we get 4y equals -x. And since x is showing up twice, we solve for things in terms of x. Yeah, I might have just convinced myself that the other way is better. I hate that so much. Do you hate it when you've been doing something for a while and you're not wanting to do it the other way, and then you're like, oh, but the other way is kind of maybe easier. So in each of these, we solve for our variables in terms of x. So I'm getting z equal to -x over 2 and y equal to -x over 4. And then I'm going to plug those back into my constraint to solve for x. Plugging into my constraint, I'm going to have, let's see, so instead of x squared plus 2y squared plus 3z squared, you could say -30 equal to 0. I would rather write equals 30. Now we plug in. We plug in z equal to -x over 2, y equal to -x over 4. So I have x squared plus 2 times -x over 4 squared plus 3 times -x over 2 squared equals 30. And now we're going to solve for x. So solving for x, let's see. I've got x squared plus 2 times x squared over 16 plus 3 times x squared over 4 equal to 30. 2 over 16 reduces to 8. And then instead of dealing with common denominators, let's just multiply everything by 8. So that's going to become 8 times x squared. 8 times x squared over 8 is x squared. 8 times 3 times x squared over 4 is going to be 2 times 3 times x squared, because the 8 over 4 is 2. And then 8 times 30 is 240. So then 8 plus 1 plus 6 is going to be 15x squared equal to 240. X squared equals 240 divided by 15, which is 16, I think. Yeah, that's right. Which is nice, because then x is going to be not just 4 plus or minus 4. And then if x is equal to plus or minus 4, y is equal to -x over 4. So y is going to equal plus or minus 4, the negative of that divided by 4. So it's going to be minus plus 1. Meaning if x is positive 4, y is -1. If x is -4, y is positive. Similarly, z equal to -x over 2 is going to give me z equal to negative plus or minus 4 over 2, which is going to be minus plus 2. So our 2 critical points, I could write annoyingly as plus or minus 4, comma, minus plus 1, comma, minus plus 2. Or I could write it more normally as the points 4, -1, -2, and -4, +1, +2. Which one's the hottest? Well, let's go look back at the original thing we were trying to maximize. We look back at our temperature function here. The temperature at, well, I really just plug in, is what I should do. So the temperature at 4, comma, -1, comma, -2 is going to be 8 plus 1 plus 6, which is 15. Similarly, if I change all those signs, then I'm going to get -8 minus 1 minus 6, which is -15. So at this point on my ellipsoid, the temperature is 15 degrees. At this point on my ellipsoid, the temperature is -15 degrees. Cool. Yeah. Oh, we should try to. So I would go back and do it the other way, except I should try to use these last 10 minutes. Time just flies. These last 10 minutes to do a 2 constraint kind of problem. So let me grab that real quick here. Is it hiding from me? No, that's a good one. Actually, I think I have one right here. Let me see. Yeah, I like this. That's pretty good. Let's do that one. So yeah. So let's say we want to, in this next one, find the point on the line of intersection of the two. I don't love that word, actually. Let me just, no, that's fine too. Let's see. Yeah, okay, that's the same problem. That's fine. Yeah. Of the two planes, y plus 2z equals 12 and x plus y equals 6. That is closest to the origin. So basically what you're saying is this point is going to be on the line of intersection. But in other words, we're constrained by the fact that this point has to be on the first plane and on the second plane. So we have 2 constraints. And then we're trying to, again, minimize the distance from the point to the origin. But really, we're going to minimize the distance squared. So minimize the distance squared, which is equal to x minus 0 squared plus y minus 0 squared plus z minus 0 squared. I should be a little bit more expository here. We're assuming the point is x, y, z, right? We don't know what it is, so we're just calling it x, y, z. And we're trying to find out how to make it the closest point to the origin, which is the point 0, 0, 0. So this x, y, z, that's our unknown point, is the point we're trying to find. And this 0, 0, 0 is just the origin. So we're trying to minimize x squared plus y squared plus z squared, subject to the 2 following constraints. Y plus 2z minus 12 equals 0. And x plus y minus 6 equals 0. And then did he give specific names he likes to use for these? Pretty standard choices are G for the first one and U or mu for the second one. Mu, yeah. Yes, I'm writing x, y, z, even though both equations don't have all 3 variables. Totally fine. And then, see, it's been a while since I've done this. And then what do we do? Okay, yeah, that's what I thought we did. So I'm pretty sure I know what we do, but not exactly. So then we're going to take the gradient of the thing that we're trying to maximize, and let's call this f. So the gradient of f is going to equal, oh, no, we don't call this mu. The thing we multiply by is called mu. Sorry, usually we call this, I don't know, like h. Sorry about that. So the gradient of f should equal lambda times the gradient of g plus mu times the gradient of h. But again, this is just convenient notation for writing a bunch of partial derivative equations. So, right, this is really just saying we want fx to equal lambda times gx plus mu times hx, which is going to be, let's see, so fx is going to be 2x equal to lambda times gx is 0. And then mu times hx is 1. Similarly, fy is going to equal lambda times gy plus mu times hy, which is going to give me 2y equal to lambda times 1 plus mu times 1. And finally, fz is going to equal, I don't really think you need to write, like, I feel like you could skip writing this equation that I'm writing here and just go to, like, I know it's going to be the gradient of, or the partial of this equals the sum of these two partials multiplied by lambda and mu. So you say, okay, the gradient of the partial with respect to z of our thing, of our f, is 2z, and it's going to equal lambda times the partial with respect to z, which is going to be lambda times 2, plus mu times the partial with respect to z, which is going to be mu times 0. And here, yeah, what is the technique for doing this? Good question. Lots of ways to solve. Yeah, what would I do here? So let's simplify these equations first, maybe. So we've got 2x equal to mu, we've got 2y equal to lambda plus mu, and we've got 2z equal to 2 lambda, or z equal to lambda. Yeah. So this is where it gets weird. I'll be really honest. Like it's always just like a, what can I see that might work? Honestly. What can I see that might work? I'm always trying to get back to, really, like, I just don't want to plug in lambda and mu to my equations. I feel like that is the worst thing ever. And I go, like, again, just personal bias. What I would do here is I would observe that 2y equals lambda plus mu. So I think I can get another equation involving just x, y, and z. I can say that 2y equals lambda, which is z, plus mu, which is 2x. Let me underscore that here. That's what lambda is equal to. That's what mu is equal to. But now look, I have this equation and I also have my two constraints. I also know that y plus 2z equals 12 and x plus y equals 6. And if you have three equations, if you have as many equations as you have unknowns, you should either be able to solve the system or see that there isn't a solution. Sometimes you get weird stuff where there isn't. Like we shouldn't not get a solution here. Like someone should have thought this problem through well enough. But it's possible that if you have three equations that all represent like planes, it is totally possible that these three planes don't intersect in one point. They could be parallel, or two of them could be parallel. One they could like, or they could just cross like in a weird like triangle kind of pattern. Right? It's totally possible for three planes to not intersect at one point. But these ones should because the problem's been done. So what am I gonna do? Good God, I don't know. I'm going to try to get this in terms of just two variable or one variable. So I've got, I like this. Sure. Here's I'm going to, no, I don't like that. Change my mind. Okay, fine. So here I'm going to say z equals 2y minus 2x. I'm going to plug that in here and get y plus 2 times 2y minus 2x equals 12. So then I have y plus 4y minus 4x equals 12. And then I can take this and say that x equals 6 minus y and plug that in here and say that 5y minus 4 times 6 minus y equals 12. So then 5y minus 24 plus 4y equals 12. So 9y equals 12 plus 24. So y equals 4. And then x equals 6 minus 4. And then z equals 2y minus 2x. So z equals 8 minus 4. Is that the way someone else would have done it? Probably not. You could probably have 3 other people do this problem totally different ways. Or at least solve this like in a totally different direction and still get to the same point. So what that means for us is that the point 2, 4, 4 is the closest point to the origin on the line, on the line that's the intersection of the two planes, on the line where the two planes y plus 2z equal to 12 and x plus y equal to 6 intersect. Neat. It is neat, but it also is just kind of like it's a lot of algebraic manipulation. You're just trying to like get these equations, play with some stuff, trying to make it work. Yeah. So I certainly, looking at the homework problems that he wrote up, it does not seem unreasonable. Like these seem like good questions. I would encourage you all to try to do these. You should certainly do the first ones first, which just have one constraint, and then the other ones next that have 2 constraints. I will probably try to do them also and post solutions to them at some point because I think it'd be nice to see them worked out. And I will, if I can, try to show both the way that I like to do where you don't really solve for lambda and the way some other people might appreciate doing where you solve for lambda.